Hello and welcome to yet another video of Cornerstones of Math. This is a rather special video in the sense that it is the 400th video on this channel. And in order to mark such achievement, I am going to calculate the value of x to the power of 400 plus y to the power of 400, given that x plus y equals square root of 2 and xy equals 1. Now some of you might come up with the quickest method right away, which in my opinion is using the polar form of complex numbers combined with a certain formula. This is indeed an effective method, but it is the method that heavily relies on advanced concepts such as polar form and complex plane, which are both outside the regular high school curriculum, at least in my country of South Korea nowadays. But this problem is more than just knowing some advanced formulas and using them, since there are other ways to solve this problem that are essentially free of complex algebra. And without further ado, let's get right on to them. In the first method, I will attempt to solve the problem solely relying on basic polynomial algebra. The basic starting idea is that there are formulas that allow us to increase the powers by a factor of 2 or 3. You know, pretty basic stuff. Using these, we can calculate the sums where their powers double or triple quite easily. But when it comes to the 400th power, we need additional formula that allows us to increase the power by a factor of 5, because 400 contains 5 as its prime factor. So how do we find this? Well, the idea is to multiply previously mentioned x squared plus y squared and x cubed plus y cubed. If you expand this, you will obtain x to the power of 5 plus y to the power of 5 from these. And from these you get x squared y cubed plus x cubed y squared. Therefore, x to the power of 5 plus y to the power of 5 is equal to x squared plus y squared times x cubed plus y cubed, then minus, we have the common factor x squared y squared, then times x plus y. And now it's time we apply the previously mentioned basic formulas. For simplicity, let us substitute x plus y with a and xy with b for now. Then this equals a squared minus 2b, and this equals a cubed minus 3ab. Therefore, this equals a squared minus 2b here, and a cubed minus 3ab here, and minus ab squared. If we expand and simplify, we obtain a to the power of 5 minus 5a cubed b plus 5ab squared. So if we convert everything back to x plus y and xy, we have x to the power of 5 plus y to the power of 5 expressed in terms of x plus y and xy, which is this formula. And now we have the complete strategy as to how to obtain the 400th power. We can obtain the 400th power by starting from the 80th power and increase it by the factor of 5. Similarly, the 80th power can be obtained from the 16th power by increasing the power 5-fold. And obtaining the 16th power is easy. We can just repeat simple doubling the power process. Therefore, we start by using the formula for the sum of squares to obtain x squared plus y squared is equal to square root of 2 squared minus 2 times 1, which gives 0. And then we compute the 4th power, which gives negative 2. And then the 8th power, which gives 2. And then the 16th power, which gives 2 again. And now it's time to use the 5th power formula. So applying this to obtain the sum of 80th powers, the formula looks like this. So we have 2 to the power of 5 minus 5 times 1 times 2 cubed plus 5 times 1 times 2. So we have 32 minus 40 plus 10, which equals 2. and then at last the sum of 400th powers. And since the sum of 80th powers is also 2, just like the previous step, the calculation is exactly the same as the previous step, which gives 2. But this is only the first method. So let us venture into another method, which is to find the recurrence relation of a sequence. That is, let x to the power of n plus y to the power of n be in for all natural numbers n. Then how do we find the value of the next term of this sequence, in plus 1? Well, inspired by the previous method, we can start by multiplying x to the power of n plus y to the power of n and x plus y. This will surely give x to the power of n plus 1 plus y to the power of n plus 1. And we also have other terms, which are x to the power of n y plus x y to the power of n. Therefore, x to the power of n plus 1 plus y to the power of n plus 1 equals x to the power of n plus y to the power of n, x plus y, then minus, we have the common factor xy, then we have x to the power of n minus 1 plus y to the power of n minus 1 here. So using in notation, we have in plus 1 equals in times I1 minus xy in minus 1. Using x plus y equals square root of 2, hence I1 equals square root of 2 and xy equals 1, the relation becomes in plus 1 equals square root of 2in minus in minus 1. Using this recurrence relation, we can obtain values of sequence in by iteration. And the thing is, this entire process also works when n equals 1. That is, this in minus 1 can be I0. Therefore, we can use I1 equals square root of 2 and I0, which is x to the power of 0 plus y to the power of 0, hence 2, as our initial values. So using these two initial values and this recurrence relation, we can find the values of in up to whatever number of terms as we want. Here, I have calculated the values up to I8 for you. But at this point, some of you might be thinking, this process is lengthy and time-consuming. So why using this method when there are other more efficient methods I can use? Well, I would say that the biggest merit of this method is that it is highly iterative. Once you obtain the recurrence relation, the rest is just doing the same thing over and over, meaning that you don't need creative thinking anymore. It's just labor. Also, in the age of computers, this property have another implication, which is that the process is easily programmable. And I gotta say, in a more complicated problem where a theoretical approach is more difficult or even impossible, the problem having this property is a huge advantage. But for this specific problem, the most important question is this. Can you find some kind of pattern here? Because in order to guess the terms having higher values of n, we need a pattern. Well, some of you might have difficult times noticing the pattern here. So I will present you 8 more terms, now up to I16. And now the pattern is more apparent. That is, the value of in changes with the periodicity of 8. Also, the values kind of bob up and down, similar to some kind of wave, but that is not important for this problem. We want to find the value of I400, and 400 equals 8 times 50. So 400 is in the form of 8 times the integer. Therefore, by periodicity, it is equal to I8, which is 2. And finally, let's get to the method that most of the viewers might consider the most efficient, using the polar form of complex numbers. But before that, we need to use the relation between roots and coefficients to find the exact values of x and y. Because x plus y equals square root of 2 and xy equals 1, x and y are roots of the quadratic equation t squared minus square root of 2t plus 1 equals 0. And by the quadratic formula, t equals square root of 2 plus minus square root of 2 minus 4 divided by 2. So we have square root of 2 plus minus, then square root of 2i over 2. And let's write this in a plus bi form, which is 1 over square root of 2 plus minus 1 over square root of 2i. Therefore, x and y are 1 over square root of 2 plus minus 1 over square root of 2i, comma, 1 over square root of 2 minus plus 1 over square root of 2i. And now let's introduce the polar form. Any complex number a plus bi can be represented by a point on the complex plane. But this point can also be determined by other parameters, namely this distance from the origin r, and this angle from the positive x-axis, theta. Then by simple trigonometry, we know that a plus bi can be also written as r times cosine theta plus I sine theta, which is called the polar form of the complex number. For our two roots, their r values or absolute values are just 1. Moreover, it is not that difficult to find that the angle theta is pi over 4, so they can be written as cosine pi over 4 plus minus I sine pi over 4 and cosine pi over 4 minus plus I sine pi over 4. And now it's time I mentioned one of the most important formulas regarding complex numbers, de Moivre's theorem. It means that for integers n, cosine theta plus I sine theta raised to the nth power is equal to cosine n theta plus I sine n theta. In our case, x and y can have values of either cosine pi over 4 plus I sine pi over 4 or cosine pi over 4 minus I sine pi over 4, and we can just write it like this, where now the angles can have either positive or negative values. So if we raise to the 400th power, then by de Moivre's theorem, we have angles multiplied by 400, so cosine 400 multiplied by pi over 4, and I sine 400 multiplied by pi over 4, so cosine plus minus 100 pi plus I sine plus minus 100 pi, which is just 1. Therefore, we know that x to the power of 400 plus y to the power of 400 is just 1 plus 1, which equals 2. And I gotta tell you, this method works really well here because in this problem, the angle theta has a really nice value. If theta is not one of those special angles, then you may have a hard time finding the values of cosine 400 theta and sine 400 theta. But of course, you can think of another method that is still related to complex numbers, because again, our angle theta has a special value. As for these two complex numbers z1 and z2, if you plot them on a complex plane, and if you already have a knowledge of the geometric implication of multiplying the unit complex number over and over, you can easily notice that z1 raised to the 8th power equals 1 and z2 raised to the 8th power equals 1. Therefore, as for x to the power of 400 plus y to the power of 400, we can simply use these 8th power values. So z2 to the 8th power raised to the 50th power. So we have 1 plus 1, which is 2. Moreover, in this case, we don't even need the polar form because the complex numbers we are working with are rather special. Using these x and y values, the sum of 400 powers is equal to 1 plus I over square root of 2 to the 400th power, then 1 minus I over square root of 2 to the 400th power. And if we actually calculate their squares first, so squared, then power of 200, so square here, and then power of 200. So as for the first square, we have 1 squared, then plus 2i plus I squared over 2. And for the second one, we have 1 squared minus 2i plus I squared over 2. Here, 1 squared and I squared get cancelled out. So it is just I to the power of 200 plus minus I to the power of 200, which can be easily calculated using the fact that I to the 4th power equals 1. So they are both 1, which gives 2. And that's all for today's video. Thank you all for watching. Please don't forget to hit that like and subscribe buttons if you enjoyed this video, and I will see you in another video.